Welcome everyone. I am Tolga Antarkan, Senior Consultant at Digitalis Consulting. In this session, I will be presenting you how we optimize AGV investments in an electronics manufacturer in Turkey with simulation modeling. We have saved more than $1.5 million of overinvestment and provided a continuous decision support system for our customer in this project. Before starting, I would like to thank all the Simio team for hosting this great event and my manager, Tolga Yanashik, for making this presentation possible. In this session, I will start with an introduction to our company, Digitalis, and myself. Next, I will be presenting the details about our project, such as the initial design, improvements, experiments, the results analysis, and so on. Digitalis Consulting was established in 2006 in Istanbul by Tolga Yanaşık. Since then, we have successfully delivered over 250 projects for more than 400 clients across 15 countries. Our clients represent a wide range of industries, with the majority coming from the automotive, manufacturing, logistics, and textile sectors. Most of our clients approach us when they are redesigning their facilities or undertaking major investment and improvement projects. For these facility layout projects, we build mathematical models to analyze material flow and identify inefficiencies. We then test various layout improvements and design alternatives. Our proposed facility layouts are not only delivered through AutoCAD drawings and Excel-based calculations, but they are supported by discrete event simulation models that offer realistic performance insights along with 3D and virtual reality visualizations. Additionally, we provide ongoing support during the implementation phase to ensure a smooth transition to the new facility design. Our services go beyond facility design and internal logistics. We also analyze and optimize large-scale, complex supply chain systems, integrating them with sales and operations planning processes. We deliver advanced production scheduling and planning solutions to enhance production capacity and improve customer service levels. In addition, we optimize inventory control strategies using simulation models, helping our clients avoid stockouts while minimizing their inventory levels. So, about me, as I said, I'm Tolgan Tarkan, a senior consultant in Digitalis. So, I'm a simulation expert, a business analyst, and data analyst. I have completed my bachelor's degree in Yeditepe University in Turkey and completed my master's degree in Jönköping University in Sweden. I have more than 12 years of experience in simulation modeling in a wide range of industries, including production systems, supply chains, energy systems, restaurant operations, and much more. So, about our case study. Our case study is about a TV manufacturing company which currently has 15 assembly lines and an aging AGV fleet of 132 vehicles, supplying from 6 AGV parking locations to 169 points on assembly lines. There are thousands of different SKUs and 27 material groups transported to the assembly lines. The production facility is quite large. We are talking about an area of 34,000 square meters, covering the assembly lines and the AG. The TV manufacturing company is initiating big investment projects. They are renewing their production facility with huge investments on automated warehouses, new paint shop, increased production capacity on assembly lines, and of course, a new AGV fleet. Even though it is not a real greenfield project, they call it greenfield due to the size of the investment. Our main focus is, of course, on the AGV fleet. The current AGV fleet is outdated. They often get stuck in the path network and cannot supply material on time, causing delays in the production schedule. Our client wants to know how many AGVs they need to order without overspending and without causing deadlock or stockouts. As you know, AGV companies aim to sell as many AGVs as possible, and their clients never know if these numbers are correct. Small AGV manufacturers also don't do detailed analysis on record number of AGVs since they need to develop complex models to prove the numbers to their clients, and they don't have resources to do so. On the other hand, manufacturing companies usually decide on their investment based on their experience, such as previously we were using this many AGVs, so in the new facility we shall order around the same number. Their decisions are mostly based on rough estimates. Deciding on the optimal number of AGVs is not an easy task, as it depends on many criteria, such as AGV specs, production schedule, supply process, bill of materials, part network, and etc. Question our customer had was not a single question of how many AGVs I need. They had many more questions related to AGV supply network, such as is the production schedule feasible? Will there be any stockouts? When should I have the changeovers? What should be how should be the supply process? When do I need to start supply of the new order? How many AGV loading stations do I need? Will there be any deadlock on the path network? Which areas will be highly congested and which areas will have the highest traffic flow? So before starting simulation modeling, we took these following steps. First, we have collected data about the facility layout and product data, such as the bill of materials, the warehouse locations, routings of materials, AGV parking stations, and then we analyze all this data and verify it with our customers. Next, we had to establish a feasible and efficient process for supplying the materials to assembly lines. Should it be a push system? Should it be a pull system? Maybe a milk run or a mix of these processes. Also, there are so many parameters that we need to decide, such as reorder point, reorder quantities for all these materials. How frequently we need to supply these materials. So this is a key input for our simulation model that will determine the outcome, and the process should also be easy to implement on the shop floor. Lastly, we have to determine our KPIs that we need to compare between the scenarios. So, what are we going to optimize? What are the key outputs that we are going to look at? We have determined our KPIs, and you will see that in the next slides. Here you see the layout of our facility. As you see, there are 15 assembly lines. Note that assembly line 12 and 13 were joined together, so now it's called assembly line 13. Also, there are 6 AGV areas, and here you see which materials are supplied from which AGV areas. There are 2 AGV fleets in the facility. AGV2 fleet supplies all the styrofoams and cardboards which are used at the end of the assembly line. AGV1 fleet supplies all other materials which are usually supplied on the rest of the assembly line. The parking locations of AGV1 fleet is on the upper side, whereas AGV2 fleet parks on the bottom side of the layout. We have determined our KPIs in line with our goal. The primary KPI is, of course, the production delay. The target value of this KPI, as you may guess, is 0. We should not have any delays occurring due to late delivery of materials. The second output we will look at is the path congestions. We will use heat maps to demonstrate where the AGVs are waiting longest in the path network and which areas has the highest traffic flow. Other KPIs that we are going to use are AGV utilizations and the time to pick up a full pallet. We will not only look at the average utilizations, we will inspect how the utilizations change throughout the simulation run. For the supply process, what should it be? Shall we use a push system or a pull system? So how does a push system work? As most of you know, in the push system, the materials are delivered to their destination as soon as the resources are available. Whereas in the pull system, there is a material replenishment algorithm which is triggered when the level of stock goes below a certain reorder point and order quantity is calculated based on some parameters. Pull system is usually associated with low inventory, whereas the push system is usually associated with high levels of stock. But we still decided to implement push system. Why? First of all, pull system is not easy to implement. There are thousands of different SKUs, all having different number of items in a pallet, which highly affects the reorder point and quantity. It is not practical to calculate optimal reorder point and reorder quantity for every single component. Even if we calculate all these parameters for thousands of SKUs, full system is still very difficult to manage on the shop floor with so many different variables for every single SKU. A push system, on the other hand, is much more easy to implement and manage. It doesn't require complex calculations for order quantities. Instead of this, we just use a time-based trigger to start the supply process for the next product before the changeover. So the only parameter we need to have is how many minutes before the order is completed should we start supplying the materials of the new order. We can also regulate the flow of push system with additional constraints, such as checking the availability of storage area next to the assembly line before releasing the transportation order. Finally, the assembly lines also have large storage area next to them, which makes it possible to implement push system. Here you can see the process that we have designed to release transportation orders for the next product. We use several data sources for this process. First, production plan, which changes daily. Second, pallet data, which is more static. And then bill of materials, routings, tag times for each product on the assembly line. By using the remaining quantity of the current order and the production tag time, we calculate how many minutes are remaining until the changeover. This allows us to trigger material supply for the new product X minutes before the changeover. In this push system, we only need to calculate one variable. How many minutes before changeover should we start supplying materials for the new order? Once this trigger is activated, AGVs pick up the materials required for the new product based on routing data. These materials are delivered to their appropriate destination. And after the delivery, the AGVs check if there is an empty pallet next to the assembly line. If there is an empty pallet, it will also pick it up and drop it off at the unloading station in the AGV area. After defining our KPIs, designing our supply process, validating the input data with customer, we are now ready to begin the simulation modeling phase. For model creation, we first built a data-oriented baseline model for the AGV supply network. We have integrated the push system that we have designed, the facility layout, and data provided by the customer into the simulation model. Once the model is developed, we verified it together with the customer to ensure it behaves as expected. This includes checking the model logic, inputs, and results for consistency and accuracy. We then analyze the simulation results to identify inefficiencies, bottlenecks, deadlocks, or stockouts. Based on these findings, we provided several improvement suggestions for the identified problems. After incorporating the improvements into the baseline model, we run a series of experiments to determine the optimal number of AGVs. The goal is to minimize the investment costs while maintaining the feasibility of the production plan. Note that for the production plan input, instead of using a historical data, we requested a hypothetical high demand schedule that the customer aims to support with their new AGV fleet. Even though the model was very large, it wasn't difficult to model with Simio, and it was also very easy to use for our customer. Thanks to object-oriented structure of Simio, we were able to define custom library objects and make changes on these object definitions when necessary, instead of editing every single instance of the object in the model. We also made extensive use of the Simio data tables. We integrated production plan, routings, product groups, and all data through the relational database inside Simio. We have created 192 supply destination objects automatically on their correct coordinates by just importing data from Excel in 1 second. We also use data tables for assigning attributes, calculations, and KPI dashboards. The material element in Simio also allowed us to define bill of materials for every single product quickly. This element enabled fast running of model by avoiding creation of a different entity for every single SKU. Here you can see the data tables that we have created in Simio. And the first table, you will see the production line definitions. As shown, we have 15 production lines, each with its assigned work schedule. The X and Z columns represent the coordinates used to position the lines within the facility window. Note, these production line objects are abstracted and do not represent every individual assembly operation on the shop floor. Instead, for our modeling purposes, the two most critical aspects of an assembly line were modeled, and these are the cycle time for the product being assembled and the changeovers that occur on the line. So by focusing on these two elements, we were able to simplify the model while maintaining accuracy for the material flow and timing of supply. Here you see our production plan table, where all the production orders and their lot size, their takt time, and sequence on the production line can be modified quickly and imported from Excel as well. Here you see the list of AGV parking areas along with their coordinates, which was obtained from AutoCAD. Here you can see our storage points, which were automatically created at the exact coordinates given in X and Z columns with the AutoCreate feature of Simio. These coordinates were also obtained from AutoCAD data, so we were able to create a significant part of the model automatically matching the AutoCAD data in just a few seconds. This is the routings table. It shows which material groups goes to which destination on which assembly line. There are 435 different routings in total. This table shows which material groups are supplied from which AGV areas. In these data tables, we have defined all the materials and the material groups. There are 387 different SKUs in just 1 day's production schedule. In this table, we have defined the bill of material for every product and also match the material group with it. So the parts can find their routes using these tables. We make use of material element in Simio to make these definitions. So we don't have to create thousands of speaker entities for a single pallet. So what is an AGV? What does an AGV stand for? AGV is the short of automated guided vehicles. They are simply driving robots that transport materials within the fixed path in a facility. They need some infrastructure such as magnetic tapes, wires, or other guided systems installed on the factory floor. A single AGV costs around $30,000 to $100,000, with an average being $50,000. So here you can see how the simulation model of the AGV system works. As you see, AGVs are leaving their locations with fully loaded pallets, and the assembly lines are producing the TVs. Currently, there are no delays. Here is an AGV working position. You can also see how many AGVs are being parked, loading, and unloading at any moment. We can see how many AGVs of each AGV group is being utilized at the moment. We can also zoom into the pallets and see their quantity, what is the material, in which location. So we can verify if it's in the right location and the quantity is correct. As you see, AGV utilization is changing every moment, and the total TV storage is also increasing. You see, at that moment, the AGV utilization had a sudden peak. Here we can zoom into our assembly lines. So assembly line is just one process, and it has just a cycle time and changeovers. So we also have the parameter of changeover trigger. So how many minutes before the changeover I have to trigger the release of the new order. So here you can see this is set to 8 minutes. And once the time remaining is reaches 8 minutes, we dispatch the new order. With the use of the simulation model, we have also identified some deadlocks and design failures. Here we can see an example of this. The engineers in the company uh, were insisting to have a single lane in this path, which I thought would cause bottlenecks and maybe even deadlocks due to long waiting times at this path. So, but the engineers were saying, oh, this should be a single lane because everybody see this part and they don't want to see a lot of traffic in this part. So even though there's a lot of space, they still want to use a single lane. But let's see what happens if you use a single lane that is bidirectional. So you see the AGVs have to queue up in order to not stuck to each other. But even though they wait here for the other AGVs coming from other direction to come back, once they go inside um, the stop location next to the assembly lines, you will see that they will get stuck there because there is a huge traffic in a very small area there. As you see, the AGVs moving in opposite directions are stuck here. And this is very hard to avoid with such huge traffic in such small area. So this was the initial design that they proposed, but we have changed this to a new design, which you can see here. So as I suggested to them, this should be like single directional, but two paths in opposite direction. So the edges will not stuck to each other in such a path. As long as they have their own track in one direction, just like a train, they will never have to wait for each other. Only in the junction points, we may have some waiting times, and we will see that in a minute. So this design works much better, and we don't have any deadlock in this design. So here we see the heat map. So we, after running the simulation, we see how many AGVs passed in each link. Here you can see some paths have a lot of traffic, a lot of AGVs passing through these parts. But this doesn't mean that they are waiting or spending most time there. You can think this place is like a highway where a lot of movement is happening, but it doesn't necessarily mean that they're spending the most time or waiting longest there. So let's see where they waited the longest. So we have another um, heat map for this. So here you see actually they go almost the same speed in all paths. But of course, some paths are a little bit thicker. So the thicker it is, the more time they spend in this part. So you see at the junctions, they spend a little more time, especially in the big junctions. There is a lot of traffic, so they might need to wait for each other. So it might be a good idea to separate some of the AGV parking stations to two. So that will distribute the traffic into different uh, junctions. So After doing these improvements, we have done a series of experiments using the experiments module in Simio. So our purpose is to optimize the AGV fleet. But not only that, we also need to know how many loading stations do we need. And another parameter that we uh, consider is the order release trigger. As you remember, based on our process, we have only one parameter, not many pre-order points, pre-order quantities for each different material. We just have a single parameter that is deciding when the materials for the new order will be released based on the changeover time. So how many times remaining to new changeover, I will start feeding the new material. So these are our inputs: the number of AGVs in each location, the loading stations in each location, and the order release time. How many minutes before the changeover I will do the order release. So when we run the simulation with the initial inputs that they have suggested, we see small delays in um, every few assembly lines. As we see, assembly line 1, 2, 9, and 11 have some delays. So the Gantt chart in Simio is very useful to see what has happened throughout the simulation run. As you see, there are many changeovers in the early morning, so they give us an intense schedule, and some of the changeovers are even happening at the same time. So there are a lot of workload on the AGVs in the morning. So you see, we can see here why the assembly line was delayed. So there are many actually components that were late, and this caused the assembly line to stop for a while. And we can see that how long it was stopped. It says 2 minutes and 36 seconds. And one of the materials that it waited longest was the artwork. But we can hover on every single product and see what was the cause of this delay. So this chart shows how the number of AGVs utilized change during the simulation run in the initial scenario. So we see that the AGV1 fleet and AGV2 fleet, they both reach their peak several times, but they don't stay in this peak level for a long time. Just momentarily they reach this peak level and then the utilizations drop quickly. So there's a lot of fluctuation, but there is a lot of times that they are reaching to the peak levels. So shall we order the quantities as the peak numbers, or shall we order a less number of AGVs? What will be the change? Here you see the results of the main KPI for our experiments. So the main KPI is the total delay. And in the first scenario, we had 23 minutes of delay for all the production lines. And we changed these control parameters, such as the number of AGVs, AGV parking areas, and of course the order release time trigger. And we have a total of 35 scenarios, and in most of the results, we get zero total delay. In this chart, we see the utilization rate of the AGV1 fleet and how it changes around the scenarios. As you can see in the first scenario, the AGV utilization is around 33%. But in the last few scenarios, we can see the AGV utilization rate is between 60 and 65%. So this is um, a range that we want to keep the utilizations at. And in this chart, you see the utilization rate of the AGV2 fleet. And for this fleet, you can see in the first scenario, it was around 40%. And again, in the last few scenarios, we reached to our target level or optimal level, which is around 65%. So we can see all the results for a filtered set of scenarios here. So one of our key inputs is the order release time, and the other inputs you can see in green color is the AGV loading stations. So we change with these numbers to identify how many AGV stands we need. And also we change the order release time to see how our KPIs change. So you can see how this KPI change along the scenarios in these slides. So in order for us to determine the best scenario, actually we want, of course, zero production delay, and we want to have uh, at least four AGVs waiting in the parking areas in each AGV area. So we need a safety uh, stock of AGVs. So some AGVs could be charging or in maintenance, they could break down, or for any reason, for peak demand, we should be keeping four AGVs at least so that we can meet these peaks in demand. So we have decided that scenario 26 uh, was around the less numbers. So that means we need just 95 AGVs compared to 132 AGVs in the beginning, which they had uh, suggested to buy. So here we can actually profit from ordering much less AGVs, around 30, more than 30 AGVs. So that's a lot of savings. As we have determined that scenario 26 has the optimal outputs of zero production delay and enough utilization for the AGV fleet and enough AGV stock. We can see what are the inputs of this scenario. So the order release time of 16 minutes was enough to supply all the materials to all the assembly lines on time. And we have also identified here how many AGV loading stands we need in each AGV station. So simultaneous loadings can happen. Uh, the AGVs can start finishing the new parts quickly without any delay. As we have determined that scenario 26 has the optimal outputs of zero production delay and enough utilization for the AGV fleet and enough AGV stock, we can see what are the inputs of this scenario. So the order release time of 16 minutes was enough to supply all the materials to all the assembly lines on time. And we have also identified here how many AGV loading stands we need in each AGV station. So simultaneous loadings can happen. Uh, the AGVs can start finishing the new parts quickly without any delay. So this chart shows the number of AGVs utilized for each AGV fleet for the optimized scenario. As you can see, we have high utilization rates in the morning because there are many changeovers coinciding in the morning time. And during the noon time, as you see, the number of utilized AGVs are dropping because there are lunch breaks on the assembly lines. And in the afternoon, we again see a peak on the number of AGVs utilized. That is because there is changeovers again for the big batch productions in these times. So you see there are peaks and lows for the number of AGVs utilized, but in the end, we did not cause any delays on the production line due to late deliveries. And in this scenario, we reached 66% of uh, average utilization for each AGV fleet. So this is kind of an optimal level that we want to have for any resource that won't be any bottleneck. With the use of Simio simulation model in this project, we have provided great benefits to our client. Firstly, we have saved more than $1.5 million just in excessive capital spending for AGV purchases. Considering an average AGV at the price of $50,000, when we order 100 AGVs instead of 132, we save more than $1.5 million in capex. Besides this, we have also avoided future bottlenecks and process inefficiencies, assembly line stoppages, which could cause also millions in OpEx. Most importantly, we have proved feasibility of the production schedule with the given set of inputs such as AGV specs, part network, and supply process. With this case study, we have provided more than just finding optimal number of AGVs to our client. The simulation tool we have developed is being used as a continuous improvement tool for testing various scenarios, including changes on part network and facility design. They are also able to see the results with different bill of material data for their evolving product portfolio. They can also test and see the results of different supply processes for a set of components. They are continuously validating the production schedule, feasibility, and making changes to it when necessary. In summary, with this single simulation project, we provided all of the following tools to our client: a CapEx and OpEx cost optimization tool, part network deadlock prevention tool, a supply management tool, a decision support for new investments, a continuous improvement tool for testing layout and process improvements, a parameter-based resource optimization tool. So you can see the value we have created just on one project in Simio. I know there are very costly software for creating just the heat maps on the path network. In this case study, heat map was just one of our outputs for the results. Thank you for listening to us. You can contact us on the information you see on the screen. Now we are ready to get your questions.